bit later. And another thing is very important is like what happens if the signal frequency is higher than half of the sampling frequency. Sorry, this should be half sampling frequency. Sorry, this what if this one is higher than the sampling, half of the sampling frequency? So you can sample them and you can recover a continuous signal, but the thing you recovered is not the original signal. We can calculate what you are going to get. So first, let's look into this process. Yeah, it is sampling and recovering one signal. So first, we have something called impulse train. So before we have a signal called impulse signal, it just have one value. Is when it's at 0, it has a value, but everywhere else it does not have have a value. So there is something like a group of them, like a train of the impulse signals is like one, another, and another. It can go minus infinite to infinite. It's a train of impulse signals. And what we see is the sampling process is like we have a continuous signal, right? And we take several points, like we take this point, and this point out as a group of numbers. It is actually the same as several impulse function signals, but they have values. It's like this one, and this one. So this impulse, a group of impulse, but each impulse has its own value. This can represent a discrete signal, even though in DTFT it is not represented as delta functions. But if you want to represent a discrete signal in continuous domain, you can represent like here by a group of impulses. So how do you get this? How do you get this spikes? You can acquire these spikes by multiply this continuous signal with an impulse train. Right? Multiply this continuous signal with an impulse train like this. Then we'll get the signal below. So this is the sampling process. And then there is another process called recovering. You can recover the continuous signal from these spikes. So, well, we see this are spikes, they are not smooth enough. So we use something to smooth it. And the best thing we can come up with is ideal low-pass filters. It's like we use low-pass filters to recover the continuous signal. And to mathematically explain this process is like you have first a continuous signal. So we just use a cosine to illustrate things in an easier way. And then an impulse train is PT. And you see this group of delta functions, each shifted by nts, and t is sampling period. And when we multiply this together, we get xpt here. So this is multiplied together, we get xpt here. And these are these modulated spikes. And then we use an ideal low-pass filter to recover the continuous signal. And it has a cutoff frequency. First we see FC, and later we see Y is half Fs. So let's try to see what is going on in frequency domain. So in time domain, it is pretty clear. We do the multiplication and then use the low-pass filter. So what is going on in frequency domain? First, it is very easy that we can calculate the Fourier transformation of a cosine function. By the way, I'm going to use the cheat sheet a lot today. So you are going to see how you can use the cheat sheet in real life. So let's go to Fourier transformation part. Continuous time Fourier transformation here. And go to cosine, and it is here, 37. we don't care about the value here. Well, because in real signal processing systems, we use amplifiers a lot. It's like you can get whatever value you want by amplifiers. So we only care about the frequency here. So let's go back here. We see x. Let's change. Xf is half delta f minus f0 plus delta f plus f0. Can I make it smaller? So in frequency domain, it is just two spikes, symmetric spikes, if this is 0 frequency and this is f. And then we want to find pf, the Fourier transformation of the impulse train. So by this one, this is not in cheat sheet, but I guess it's, well, it's in cheat sheet here, 40. And we found out that the Fourier transformation of an impulse train is still an impulse train. So this is half t0, and here t0 is ts, and we know not half, it's 1 over ts is the sampling frequency. So here it is, we define fs is 1 over ts. So we got fs here, sum from minus infinity to infinity, delta f minus n time fs. So if we plot it, it is an impulse train, and looks like this. So here, this one is fs, this is 0, this is minus fs, and actually we have infinite number of it. And xp, so in frequency domain, xpf, because here is multiplication, here it will become convolution. So it is xf convolution pf. And we see they are all impulse delta functions. When you do convolution with a delta function, that means you're shifting it. So let's see fx as a signal, and each spike of pf is a shifted delta function. So we're going to shift xf to the position of each spike in pf. So what we are going to get is something like this. Around 0 at the center, we have one spike, another spike. This is minus. By the way, this is f0, this is f0, minus f0, and here is f0. And around fs, we're also going to get two spikes. And this spike is fs minus f0, and this is fs plus f0. Also, we're going to get two spikes around minus fs. Minus fs minus f0, and minus fs plus f0. So you see this pattern of xf is copied at each location of pf. So we see this is a periodic signal in frequency domain, and the period is here. The period is fs. So we want to get the original signal from this signal by a low-pass filter. A low-pass filter is going to cut the centerpiece of the spectrum. And we know that this is a periodic signal, and it has many periods, and the center period happens from minus half fs to half fs. So we cut this centerpiece out by an ideal low-pass filter. So an ideal low-pass filter will cut this part out. So the spectrum of FRF without any math. I just cut this piece out. So I'm going to have 0 and F0, F0, this is minus, and everything else is removed. So why we get half Fs? Because from minus half Fs to half Fs is one period of the periodic spectrum. And by the low-pass filter, we're going to cut the center pieces. And this one is similar to the original signal, but this one is original signal only when this F0 located inside the ideal low-pass filter. That is when the signal frequency Fs is less than half Fs. So, any question about it? So the next question is, what if it does not satisfy this condition? So if we got a signal look like this, minus F0, F0, and the sampling frequency is like this. This is the sampling frequency, Fs. And when we copy the pattern at these locations, we're going to have something like this. I'm going to use different color for different period. So for the center period, we have this. And for the one on the right, we have this. Oh, this is far away like this. And for the one on the left, we have this. And if we use low-pass filter to cut the center, sorry, I need to label these frequencies. So this is F0 minus F0, and the purple one here, this is Fs, and this Fs minus Fs plus F0, and the green one is Fs minus F0. So if we use a low-pass filter, that's going to cut half Fs on each side. So it's going to cut this piece out. So after the ideal low-pass filter, we're going to get two spikes, but these spikes are not the original two spikes. These are minus Fs plus F0 and Fs minus F0. So if you write that mathematically, XRT equal to, or I should say proportional to, because the amplitude we don't care it so much, it is cosine 2 pi Fs minus F0 t. So this is not the original signal we got. Any question? So then we can do that without any math. We can try to recover a signal. So when sampling frequency is 200 Hz, and we know that half Fs is 100 Hz. So what will happen if the input signal is like one component is 130 Hz and the other component is 830 Hz? So we know that they cannot be recovered because they exceed half of the sampling frequency. So what will happen? So basically what we are doing is we want to try to find the components inside the center period. So what we are going to do is we want to find, for example, 130 Hz plus 2 plus k times 200, and we want to find a k that can make this number between minus 100 Hertz and 100 Hertz. Then we want to try out all the k's we have. So because 130 is something higher, so we want to minus 200 to try this first. 130 minus 200, and we got minus 70 Hertz. And this is in between minus 100 and 100. So what we are going to have when we recover the first term, we're going to have something like cosine 2 pi 70t. And second part is 830. So 830 we first minus 200. Try it. Yeah, we got 630. This is still pretty high. So we keep doing this until we got something like 830 minus 4 times 200 is 30 Hertz. So the second component will become cosine 2 pi 30t. So after recovering from a low pass filter, we're going to have xrt equal to cosine 2 pi, sorry, not equal to, is still proportional to 70t plus cosine 2 pi 30t. Oops. Question?
Are we just ignoring the k?
Which k?
The k is
Oh, the k is like I'm trying all the k's and until I find a number in between minus 100 and 100. It's like for this answer the k is just minus 1, and for this answer the k is minus 4. But k is not very important. The final answer is important.
And is that negative 70?
Negative 70 is the same as 70. Well, it's not always true, but usually it's true because usually we only have the signals that are symmetric. So any question?